Hello and welcome to Chem 100 lecture. It is Tuesday evening, and we're ready to get to it. So we are going to begin chapter 3. Yeah, we're starting chapter 3 today. Just double checking my lecture notes. Chapter 2 was a little bit on the shorter side, as was Chapter 3. Chapter 4 will take us a little while to move through. So yeah, let's go ahead and dive right in. Now, the main player in Chapter 3 is the periodic table. We're going to be getting familiar with this thing. We're going to be using it a ton. And so it is going to be front and center. Now, there are just a few things that you need to be aware of and familiar with respect to the periodic. And that is, so a little bit of nomenclature. When we talk about there's the periodic table is a square grid, right? There's the vertical and the horizontal components, the vertical columns, the horizontal rows. Now, every column on the periodic table is called a group. So when we refer to groups of the periodic table, we're talking about specific columns. And every row, oh, there's a little drift there. Every row on the periodic table is called a period. All right, so we have our groups, we have our periods. We talk about there are trends along the periodic table that develop as you move across a period, and every group on the periodic table shares certain properties, certain chemical properties. Groups tend to share those in common, and periods you tend to see trends across a period as you move from one side to another. All right, so groups are vertical, periods are horizontal. Now, there is a term that you should be familiar with. It's called periodic law. And it's a very simple principle. I'm going to give you kind of a simplified version of it, but simply stated, periodic law says that elements of the same group I should say not have, but share similar chemical properties. Oops. All right. Elements of the same group share similar chemical properties. So when you look at every column on the periodic table, the elements that you find in a column will have certain traits that they share in common with the other elements in the same group. All right, now there are a few different ways to slice up the periodic table. I want to introduce them now, and again, because your exams are open note, open internet, open book, open everything, right? These aren't things that you have to memorize, but these are things that you need to be familiar with, and I just kind of want to give you kind of a feel for the different regions of the periodic table. The first that I want to draw your attention to is the difference between metals and nonmetals. So Some periodic tables have a sort of dividing line. This one doesn't, some of them don't, but most of them do. If you're looking at a periodic table that doesn't put a visual barrier in between the metals and the non-metals, you can always add it artificially by drawing a line in between boron and aluminum, and then stair-stepping your way down. All right, so you can, if your periodic table doesn't have kind of that barrier included, you just find boron and aluminum right there, and then stair-step your way down. All right, now everything, all the elements to the sorry, directions are hard. To the right are going to be are your non-metals. All right, so your non-metals are all over here. There's only one notable exception to this, one non-metal that isn't clumped over here with the rest of them. And that is hydrogen, all right? But that should come as no surprise. Hydrogen, as we know, is a gas, right? So hydrogen is it's the first element on the periodic table, so it's all the way to the left, but excuse me, hydrogen is not a metal. So over here, we have non-metals over here. Let's keep our color coding. Our non-metals are here and here. All right, on the other side of the railroad tracks, we have our metals. All right, so all the way over here, this whole region of the periodic table, these are all metals. And as you can see, there are far more metals on the periodic table than there are nonmetals. All right, so the orange region is metal, the lavender region is non-metal. You'll notice I left off all of the elements touching that dividing line, all right? Turns out the concept of metal and non-metal is somewhat artificial. It's something that humans created. They're categories we created based on behavior we saw in nature, right? But there are some metals, but it's not an on and off switch. There are some elements that kind of have some metallic qualities, some non-metallic qualities, and so these elements that kind of fall on the in-between, they're somewhat transitional in their behavior. They have some metallic qualities and some non-metallic qualities, and these elements we call the metalloids. These are metalloids. Right, one metalloid that you'll notice right in here is silicon, right? And silicon's a great example of a metalloid because I said metalloids have metallic and non-metallic properties. Metals conduct electricity, right? All of our wires are made of metal. Non-metals do not, they're insulators. And silicon, for example, being a metalloid, is neither a pure insulator or a pure conductor. It's a semiconductor, right? And we use it to make all of our computer chips. So that's a great example of a metalloid because it has some metallic and non-metallic properties in this weird kind of fusion liminal space. All right, so this is one way to divide up the periodic table into metals, nonmetals, and metalloids. But it is not the only way to divide up the periodic table. All right, we're going to look at two additional ones. You may notice that in this periodic table, we kind of have this weird sort of drop-off region, right, where things kind of fall off. But then it picks back up on the other side, right? And so these kind of two halves of the periodic table, these are known as the main group elements. Kind of either side of the periodic table, here and here. All right, and then this area down in the middle, these are our transition metals right here. These are called transition metals. And if you're wondering, okay, well then what's this region down here? These are neither main group elements or transition metals. These are called the Lanthanides and Actinides. All right, I'm so sorry. My kids are being really loud. I will be right back. There we go. Sorry about that. Nothing is more exciting than being 12 years old and watching anime. All right, so we have our lanthanides and actinides floating down below. They're not as important. Well, I shouldn't weight any of these things with importance, but we're going to spend far more time in this course looking at the main group elements versus the transition metals. More of that's to come. Finally, the last kind of way we can divide up the periodic table is into blocks. All right. Now, the first two columns, and really helium is a part of this. You'll see why later. This is the S block. All right. The transition metals down here. This is known as the D block. The second half of the main group, all up in here. This is the P block. And then our lanthanides and actinides, this is known as the F block, or flock. All right, so, we will be using this way of looking at the periodic table a ton when we get to electron configurations, which will be relatively soon. Okay, so these ways of looking at the periodic table, this is more to like orient you. So you know what I'm talking about when I talk about groups versus periods, when I talk about metals versus non-metals, or main group elements, transition metals, or specific blocks, S block, D block, P block especially. These are things to know and things to be familiar with because this is nomenclature. These are names that we're going to be using, and that will, you knowing them will kind of lubricate and facilitate our discussion of the topics ahead. All right. We will come back to the periodic table soon. But first we need to do a little bit more groundwork. All right, so when I say the word atom, you probably are thinking of the symbol for the International Atomic Energy Agency, right? Is that the thing? The nucleus with all the atoms spinning, or sorry, electrons spinning around, right? And so that's probably the first thing that comes to mind, and that model of the atom has a name. It's called the Bohr model of the atom. So you've got the proton in the center, in the nucleus, and then you have an electron orbiting the nucleus. And this is probably the first visual that comes to mind. Not a bad one to have in your head. So this is called the Bohr model. The Bohr model of the atom, and it's the one that kind of, like I said, we first think of. One of the interesting features of the Bohr model, that this is what we think of, but it's actually not the entire Bohr model of the atom. One of the more interesting features, and this is what led to the development of quantum theory, is that the electron is orbiting the nucleus, but it does so in specific orbits. So it turns out the electron isn't free to orbit the nucleus just anywhere it pleases. It can only occupy set, defined regions in space. And we call, so it can either be in this first one, which we label n equals 1, or it could be orbiting in an outer orbit, n equals 2, or n equals 3, or n equals 4. They get larger and larger and larger, farther and farther from the nucleus. All right, and the letter n is what we use to label the energy level of the electron, and the value for n tells you how close or how far the electron is from the nucleus, and n, that number, is called the shell. All right, it is called the electron's shell. Whoops, did not mean to cross that through. There we go. So when we talk about the shell of the electron, we're talking about the value it has for n, and that tells you how close to the nucleus the electron is. The smaller it is, the closer it is, the larger it is, the farther it is. Now, when you think about the electron and the proton, these two particles are attracted to each other. All right? These two particles are attracted to each other. And so, if you have an electron, that goes from being in the first orbit to the second orbit, let's say it moves away, because it's attracted to the proton, to get it to move away, you have to pull it. You have to invest energy. If you move from the first shell, a lower shell, to a higher shell, to do that means that the electron gains energy. all right, when you go from a lower orbit to a higher orbit. If, let's say you have an electron that starts at a higher shell, we'll say it starts at on the fourth shell, and it moves to a lower shell. Well, let's do shell number 2. If it starts far away and then moves closer, that's the direction it wants to go. If you let go of the electron, it's going to move as close to the nucleus as possible. So when you go from a higher shell to a lower shell, your electron is going to do the opposite of gaining energy. It releases energy. All right. So we have, when you're at a higher shell, that is a higher energy state, because when you move from a lower shell to a higher shell, you've gained energy. When you go from high to low, the lower shell is a lower energy state, so it releases energy when it moves in that direction. All right. Now, as I said earlier, the Bohr model is the first thing that pops to mind. It's not a bad place to start, but it was an insufficient model. It couldn't actually explain all of the data, and it eventually got replaced because it couldn't account for all the phenomena that we see in nature and with atomic behavior. And so it ends up getting replaced by what is our current model, our current theory of atomic structure, which is the quantum mechanical model. And one of the things that the Bohr model got wrong is the Bohr model assumed that the electron moved in a two-dimensional orbit, like in a circle or an ellipse, when in fact it does not. The electron is free to move through three-dimensional space, as are we. The thing is, it got the energy levels right. The shells of the Bohr model were correct. It's just the two-dimensional nature of the orbit was incorrect. So the Bohr model ends up being replaced by the quantum mechanical model of the atom. All right, it ends up getting replaced by the quantum mechanical model of the atom. And in the quantum mechanical model, there's more than two key features that differentiate it from the Bohr model, but the two key features that we are going to focus on in this class, two things to set it apart. First is that in the quantum mechanical model, electrons move in three-dimensional orbitals, not in two-dimensional orbits. All right, and then the second feature that kind of launches us ahead is in the Bohr model, there's only one type of orbit. I mean, there were multiple shells, but they were all circles, right? In the quantum mechanical model, there are 4 different orbital types. All right, there are 4 different orbital types. There is the s orbital, all right, so this is the s orbital, and there is one s orbital per shell. So on any given shell, there is one s orbital. So on the first shell, there's a 1s orbital, 2s orbital, 3s orbital, etc. Every shell has one s orbital. There is the p orbital, and the s orbital, as you can see, looks spherical. The p orbital is three-dimensional on both sides, but one side's shaded in. Kind of looks like this weird dumbbell balloon animal. On every shell with a p orbital, there are 3 p orbitals. So on the second shell is the first shell where p orbitals appear, and there are 3 p orbitals on the second shell. There are also 3 p orbitals on the third and the fourth, etc. The next orbital type is called the d orbital, and it kind of looks like what you'd get if 2... Oh, that's a little sloppy. Let's see if we can do that better. If you kind of made an X out of 2 p orbitals. So this is called the d orbital, and on every shell with a d orbital, there are 5. So the third shell is the first shell where you see d orbitals. There's 5 of them on the third shell, 5 d orbitals on the fourth shell, 5 on the sixth shell, etc. Finally, there is the f orbital. And you'll notice that with each orbital type, we have more and more of them, and F is no exception. There are 7 F orbitals on every shell where they occur. So the first shell that has F orbitals is the fourth shell, and there are 7 of them there. If you're wondering what they look like, they look gnarly. Way too gnarly for me to draw. So if you want to see what they look like, I recommend you Google it. All right. So these are the 4 types of orbitals. And part of the reason why I spent some time drawing them out is because knowing what they look like actually tell you something about their energy level. The S orbital is the simplest type, and it is the lowest in energy. The F orbital is the gnarliest type, and it is the highest in energy. And the p orbitals and the d orbitals energy levels lie in between these two. So that's one of the reasons why I kind of like drawing them out and visually depicting them for you, not just so you know what they look like, but that picture tells you something about the energy level. All right. Now, we're going to transition into talking about electron configurations, and orbital diagrams. All right. Before we do, I'm going to give you something for your equation sheet on your exam, something that you want to keep on the ready that will help you as we work through these problems. I won't have enough room to leave it on the whiteboard, but maybe you open another tab with YouTube in it and pause the video when I finish writing this out, when they're all displayed, and you can use that as a reference to solve these problems. You want to have one of these at the ready when you're doing the homework problems, even while you're taking the exam. It'll come in handy. Now, I mentioned something when I was drawing out the orbital shapes. I in addition to telling you how many of them there were, I said like, oh, the second energy level, second shell is the first shell with p orbitals, or fourth shell is the first shell with f orbitals, etc. And so you may be wondering, well, how do I know how? Like, that sounds confusing, and so I'm gonna show you. I'm gonna give you this to help you as you work out these problems. So here's a y-axis with energy on it. On the first shell, when n equals 1, there is 1 single s orbital on the first shell. When you move to the second shell, all right, higher in energy, on the second shell there is 1 s orbital and there are 3 p orbitals. On the third shell, there is 1 s orbital, 3 p orbitals, 5 d orbitals, and that's it. And then on the fourth shell, there is 1 s orbital, 3 p orbitals, 5 d orbitals, and 7 f orbitals. All right, and so this is collect this a little bit. So this is something to keep in mind as we do electron configurations. It might help you, especially at the beginning, kind of sort through the kind of the flow of logic. All right. So you need this to keep this in mind. What orbitals are on which shells as we write out these electron configurations. You also need to keep there's 3 principles that you need to keep in mind as we write these electron configurations. And I know I haven't told you what electron configurations are. I'm going to in a second. But first I just want to get these out written down so you can have them as reference. And then I'll tell you what they are, and then we'll start doing the examples, because that's the best way to learn them. All right, so the 3 principles you need to write electron configurations. Number 1, you need to know that the lowest energy orbital or orbitals fill with electrons first. I should say fill first with electrons. All right, number 2. So first, the lowest energy orbitals fill first. Second, actually, a little word for space. The second is what's known as the Pauli exclusion principle. All right, the Pauli exclusion principle states that one orbital can hold a maximum of 2 electrons. All right, so 2 electrons, 2 is the maximum number of electrons that fits in one orbital. The third is something known as Hund's rule. Hund's rule? There's a D on there. It makes it difficult to pronounce. Hund's rule states that electrons, or I should say, because electrons repel each other, they only share orbitals when they have to. They're like kids. They only share a room when they have to, right? When you've run out of space elsewhere. And we'll see examples of all of these as we, as we start doing some of these examples. So these are kind of the ground rules. I'm going to be applying these. I recommend you open this in a second tab so you can have it to reference as we dive in. Before we do, I want to tell you what electron configurations are. What is this thing that I'm about to teach you? All right, electron configurations are they're a depiction, they're a representation of the what's known as the electronic structure of an atom. All right. They represent the electronic structure of an atom. In other words, they tell you the location and energy level of each electron orbiting the nucleus. All right, and we are going to learn how to write them for every element on the periodic table. Any element on the periodic table, by the time we're done, you'll be able to write the electron configuration for it. Actually, that's not true. If this were Gen Chem, you would. There's actually a region of the periodic table I'm going to stay away from because the book kind of shies away from it. We're not going to look at the F block. So, which the good news is you don't have to deal with the most complex cases. So we're going to look at almost all the elements on the periodic table. You'll be able to handle. If you want those that last like 10%, take general chemistry and you will have the opportunity to learn them. All right, so that's what an electron configuration is. It is a depiction of the electronic structure of an atom, and it will give you the location and energy level of every electron orbiting a nucleus. Sounds pretty cool if you're, well, a nerd. Let's talk about how to write them. All right. Well, I need my periodic table. I'm going to move it over just a bit. So let's start, to quote Julie Andrews, at the very beginning, which is a very good place to start. If you didn't get that reference, go watch The Sound of Music. Oh, Christopher Plummer just died. He's an actor. He's the actor who's the captain, the main love interest in The Sound of Music. He just passed away. Let's write out the electron configuration for hydrogen. Now, you'll notice that hydrogen has one electron, all right? Hydrogen has one electron. So given, and this is where you want to reference that page where I wrote out all the energy levels and the rules, Pauli exclusion, Hund's rule, etc. Given hydrogen has one electron, and our first rule, our first guiding principle is every single electron wants to occupy the lowest energy orbital possible, where do you think that one electron is going to go? It's going to see if there's room in the first shell, which there is, right? We haven't housed any electrons yet. There's room in the first shell. And so it's going to occupy the 1s orbital, right? The s orbital on the first shell. Now, I'm going to break this down for a second here. I'm going to tell you what these numbers mean. First off, this leading number right here tells you the shell that the electron's in. So that big one in front tells you first shell. All right, this symbol, this S symbol right here, tells you the orbital type that the electron is housed in. The orbital type is often called the subshell. So we would say that this is literally the S subshell. All right, this electron is in the S subshell on the first shell. Finally, this superscript right here tells you the number of electrons in that subshell. So looking at the electron configuration for hydrogen 1s1, it tells us that we have one electron in our S subshell on the first shell. All right, that's how you read it. That's how you unpack the information. Let's write the electron configuration for helium. All right, now helium has 2 electrons, all right? We know where the first electron is going to go, right? It's going to occupy the S subshell on the first shell. Where's the second electron going to go? Well, the Pauli exclusion principle tells us that each orbital can hold a maximum of 2 electrons. So there's still room in that first shell to hold our second electron in helium. So the electron configuration for helium will be 1s2. Again, that superscript of 2 tells us that there are 2 electrons in the S subshell on the first shell. Let's look at lithium. Lithium has 3 electrons. Now we know where the first 2 electrons are going to go for lithium. They're going to go into the S subshell on the first shell. But the third electron can't fit, right? In one orbital can hold 2 electrons max, Pauli exclusion principle. So our third electron can't fit on the first shell. And there's only one S orbital on the first shell. So our third electron has to look at the second shell. Now we have a decision to make, because on the second shell there are 2 subshells, right? There's the S subshell and the P subshell. Which subshell is our electron going to go for? All right? And it goes for the one that's lower in energy. We know that S is lower in energy than P. So our third electron will be held in the S subshell on the second shell. So the electron configuration for lithium is 1s2, 2s1. All right, let's skip ahead a little bit. Actually, I need to save my space. So I'm going to move these up just a little bit. All right, let's write the electron configuration for carbon. Carbon has 6 electrons. The first 2 will go into the first shell, the S subshell. Next, now we're on the second shell. We have a choice, P subshell or S subshell, and you always go for the lowest energy orbital first. So we're going to fill up the 2s subshell. Now, we have 2 electrons in the 2s subshell. Our next 2 electrons have to go into the 2p subshell. So we put a 2 out in front, a p, then we put 2 electrons into the 2p subshell. So this is the electron configuration for carbon. Let's look at oxygen. Oxygen has 8 electrons, right? We have 8 electrons in play right now. Our first 2 will house in the 2s subshell, sorry, the 1s subshell. Our next 2 go into the 2s subshell. And our remaining 4 go into the 2p subshell. So this is the electron configuration for oxygen. Now, you may want to cry foul. You may say, wait a minute, Pauli exclusion principle says that only 2 electrons can be held in an orbital, and you are absolutely correct. You may be coming back at me and saying, Josh, well, if one orbital can only hold 2 electrons, why did you put 4 in your 2p subshell? And my answer to you is exactly that. This is not one p orbital. It is the 2p subshell. Remember, there are 3 p orbitals in every p subshell. So because there are 3 p orbitals in every p subshell, you can see up to p6, because each of those orbitals holds 2 electrons, all right? 3 p orbitals in every p subshell. So in electron configurations, you could see anywhere from 1 to 6 electrons in any given p subshell. All right, now, we've got a couple more examples. Let's do neon. Neon has 10 electrons. Our first 2 will be housed in our 1s subshell. The next 2 will be housed in our 2s subshell. So we've housed 4 out of our 10. We have 6 left, and guess what? 6 will fit in the 2p subshell. All right, now, next example, we're we're going to do sodium. Now, sodium, you'll notice, has one more electron than neon. All right, it has one more electron than neon. That means that sodium is going to have the electron configuration 1s2, 2s2, 2p6, plus 1. Plus 1 going somewhere. We've got to figure out where that 1 goes. Now, here's the deal. It's not going to be 2p7 because there are 3 p orbitals in the p subshell. It can't hold more than 6. If you look at that chart, that little graph that I made a little while ago, you'll notice that on the second shell, there's only an s subshell and a p subshell. That means we got to kick up to the third subshell. So wherever this is going, it's going to be 3 something. Now on the third shell, you got 3 subshells available, S, P, and D. You always want to pick the lowest energy shell. So it's going to go into the S subshell on the third shell. So the electron configuration for sodium will be 1s2, 2s2, 2p6, 3s1. All right. Now, you may be going, okay, Josh, this is kind of getting painful. This is kind of getting painful. I mean, it was easy to do sodium because we had just did neon, but what if we hadn't? We'd have to figure out where all these electrons are going to go, all that stuff. Is it going to be that bad? And my answer to you is it's going to be worse. It's going to be worse when I ask you to write the electron configuration for xenon, who has 54 electrons. And you might be thinking, but you wouldn't do that, right? That would be mean. No, I totally will. I totally will do it. It is going to be worse unless you learn the shortcut that I'm about to teach you. I'm going to teach you a shortcut that's going to make writing these out way more fluid, much more simple. You won't have to go through this agonizing process of housing each electron individually. I just wanted to give you a sense of why we need this process, also where it comes from. But it's not going to be brutal if you learn this shortcut. All right, let's see. Rocks. Excellent observation. Oops. Rocks, that is 100% correct. As long as your electron count is 10 or less, it'll fit on the second shell. Totally. But once you hit 10, you've maxed out the first and the second shells together, and you got to bump up to the third. All right, now what is this wonderful, amazing shortcut that I've been teasing? Here's the shortcut. You'll notice that sodium has all the electrons that neon has, plus a little more, right? But it's almost like there's an entire neon atom contained in sodium, plus this one more buzzing around the outside. This gives rise to what is known as the noble gas abbreviation. What the nomenclature that chemists have developed is this. You're allowed to say, okay, you're allowed to use the noble gases as your abbreviation. If you're going, what are the noble gases? I'm so glad you asked. They are the last group on the periodic table. These are the noble gases. All right, if your element has more electrons than one of these noble gases, you can write the electron configuration by writing its nearest noble gas with fewer electrons in a bracket, and then writing the extra electron. So since sodium's nearest noble gas is neon, then that means we can write the electron configuration for sodium by putting neon in a bracket and then saying, okay, it's all the electrons of neon plus one electron in the 3s orbital. All right. This right here and this right here each have a name. The electrons that are contained in the noble gas configuration, these are called the inner or core electrons. And then the electrons that are outside the noble gas abbreviation, the extra ones built on the outside, these are called the valence electrons. All right. And the valence electrons are the most important ones in chemistry. They are the electrons in the highest energy shell. All right, the electrons in the highest energy shell are the valence electrons. All the rest are the inner core electrons. All right. Now we are going to do a ton more practice with, we're going to do a ton more practice with electron configurations. But before we do, I want to talk about the second half of our banner up here. I want to talk about orbital diagrams. All right. Now, an orbital diagram is just another way of depicting the information that an electron configuration already gives us. In an orbital diagram, so in the and it's just, one isn't better or worse, they're just different. They're different names, different ways of depicting the same information. Now, in an orbital diagram, or I should say, in an electron configuration, all the orbitals in a subshell are clumped together. All right. In an orbital diagram, individual orbitals within a subshell are each represented, and they're represented with a line, and then they're labeled. So this represents the one orbital within the, actually I'm gonna color code this different. This represents the one orbital within the 1s subshell, and the electrons are represented by arrows. Now there's one electron in the 1s orbital, so that means we draw one arrow in the 1s orbital in our orbital diagram. Note, I draw my electrons like this with just half an arrowhead. You can totally draw them with 2 arrowheads. That's completely fine. Neither is right or wrong. Just so you know. So this is, oops. Actually want to scoot this up just a bit. So that's the 1s, that's the orbital diagram for hydrogen. Let's write out the orbital diagrams for each of the electron configurations that we have here. So for helium, again, we're dealing with the 1s subshell, and we have 2 electrons here. So we put them both in the 1s subshell. Something you should notice is we say that one of the electrons is, this is called spin up, and the other electron is spin down. This is a phenomenon that we get from quantum mechanics. I'm not going to dig into the calculus behind it here, but when you have two electrons in that are occupying the same orbital, they must have different spins. It's impossible for them to have the same spin. Spin is a phenomenon created by the magnetic field generated by the charged particle as it moves through space, and it's a pairing thing. When one's up, the other's down, and vice versa. You'll never have both up, you'll never have both down. They're always what we call spin paired. One up, one down, all right? So if you have two electrons both pointing up or both pointing down, you'll totally lose points on an exam. That is an incorrect answer. So make sure that one is spin up and one is spin down if they're in the same orbital. All right, let's draw the orbital diagram for lithium. Now, here, this will be our first orbital diagram with different, or sorry, not different, well, yeah, different, but with more than one orbital. We need to label each orbital with its shell and subshell. So our first is our 1s orbital, our second is our 2s, and you'll notice here that we have 2 electrons in our 1s subshell, and we have 1 electron in our second. All right, so that is the orbital diagram for lithium. Let's jump to carbon. So we have our 1s subshell, our 2s subshell, and our 2p subshell. Notice in your orbital diagram, you represent every individual orbital within the subshell. So when you're dealing with a with a p subshell, you have to draw all 3 p orbitals out within that subshell. In our 1s subshell, we have 2 electrons. In our 2s subshell, we have 2 electrons. In our 2p subshell, we also have 2 electrons. Now, you've probably forgotten about this because we haven't used it yet, but this is the first example where Hund's rule comes into play. Remember how with Hund's rule, when we were first writing them out, we said that electrons do not share orbitals unless they have to. In the previous examples, they had to because you always fill the lowest energy orbital first. But here's the thing. In the 2p subshell, you have 3 different orbitals, and they all have the same energy. Because they have the same energy level, your electrons will not share an orbital. One's going to be in one p orbital, one's going to be in another. And they're not going to share because they repel each other. They're like kids. They're not going to share a room unless they have to. All right? You'll notice also that these are both spin up. When you have electrons that are in different orbitals, they'll always spin pair. All right? Just like magnets will line up with each other, they will always spin pair when they're in different orbitals. All right? Let's see what happens in the next example. So oxygen, we have our 1s, our 2s subshell, and our 2p subshell. All right? We have, let's get our color coding. 2 electrons in our 1s subshell. We have 2 electrons in our 2s subshell. And we have 4 electrons. Now, when you're filling up your 2p subshell, remember, electrons don't want to share a room. They only do if they have to. We've got 4 electrons to house. We put 1, 2, 3 in, but now we have a 4th. The 4th has to go in one of these orbitals, so 2 of these have to pair up. All right. this is what happened to me when my brother was born. So I'm the oldest of 4. And so I'm the oldest. Second was my sister, and my mom, my dad, and my sister. We lived in a 3-bedroom place. And so I had a room, my sister had a room, my parents had a room. When my parents got pregnant with my brother, number 3, he got put in my room, and now it wasn't my room anymore. And that's what just happened with this electron right here. I'm not going to put an arrow, that's actually slightly confusing. But we ran out of individual rooms. We're not buying a new house. We're just doubling up a couple other kids. That's what happens. That's what's about to happen to my kid. So I've got 3 actually. And the youngest is 2, and we have 1 more on the way. And so the infant is going to go into the 2-year-old's room. That totally makes sense. So this electron situation is about to happen domestically for me and our family coming in July. So that's what happens when you have to. They'll double up. If not, they'll all be separate. Let's do neon next. So we have our 1s subshell, our 2s subshell, and our 2p subshell. We have 2 electrons in our 1s subshell, 2 electrons in our 2s subshell, and now we've got 6, a whopping 6 electrons in our 2p subshell. So we have 1, 2, 3, 4, 5, 6. Everybody's paired up. That's what would happen if my family, if my wife and I had 2 more kids. We're not planning on it. I think 4 is a good number. But anyways, if you keep having kids, more electrons double up. It's the moral of the story. Now, let's look at sodium. Now, we said one of the differences with orbital diagrams is you draw out every orbital individually. Another kind of benefit, if you will, to orbital diagrams is you only have to draw out the valence electrons. So because we're using the noble gas abbreviation here with neon in brackets, we don't care about the inner core electrons. All we care about are the valence electrons, because the valence electrons control the reactivity and the behavior of the molecule. So for the orbital diagram, just do the valence electrons in the orbital diagram. Valence electrons wise, for sodium, we just have 1 electron in our 3s orbital. So that is the orbital diagram for sodium. All right. Let's see how we're doing. Okay. I'm going to do a few more examples. We've got about like 15 minutes left in class, and then we will break, come back and do lab, at least for section 60. I want to show you how to use the periodic table to your greatest advantage. All right. I want to show you how to use the periodic table to your greatest advantage. Now, to do this, let's just pick, let's do nitrogen. All right. Step number 1 is find nitrogen on the periodic table. All right, it's right here. Step number 2 is locate your nearest noble gas. Actually, I don't want to start with nitrogen. I want to start with, sorry, nitrogen. We'll come back to you. We'll do you in a second. Let's start with magnesium. You find magnesium on the periodic table and then locate its nearest noble gas with fewer electrons. Because magnesium has all the electrons of neon plus some, you're going to begin writing its electron configuration by throwing neon in a bracket because it has all the electrons of neon plus a few more, right? That's step number one. Step number two is identify the block that magnesium falls in. This gets back to that thing we were talking about at the beginning of lecture. Magnesium is in the S block. All right? Magnesium's in the S block, which tells you that magnesium is going to have its highest energy electron in an S subshell. You're like, really? Yeah. The block that an element is in tells you where its highest energy electron is. The subshell that its highest energy electron is. Now, so you may be going, okay, subshell's great, but what about the shell? To determine the shell, count your period. Notice that magnesium is on the third period. That means it's in the third shell. This is the 3s subshell. You're like, that's crazy. But what about the electrons? How many electrons are in its 3s subshell? I'm so glad you asked. What you do to find the number of electrons in your subshell is start at the very edge of the periodic table and count your way over to the element in question. 1, 2. Magnesium is 2 spaces in to the 3s subshell. So it will have 2 electrons. So the electron configuration for magnesium is neon 3s2. You got all of that information straight off the periodic table. All right. Let's do another example. Let's do nitrogen. Now we'll do nitrogen. All right, step number 1, we've got to find it. It's here. Where's our nearest noble gas with fewer electrons? That's helium. So we're going to start by throwing helium in a bracket. All right, next, we're going to find the period that nitrogen's on. Oh, sorry. My bad. Sorry, I just saw your comment just now. Yes, for the previous example, it's got a 1. So we find our period that houses nitrogen, and it is on, so nitrogen is on the second period. All right, now you always start on the very edge. All right, start right here, and we need to count our way over to where nitrogen is. So we count 1, 2 spaces over into the S block. So this will be 2s2. But now we need to get to nitrogen. We need to jump from the S block over into the P block. Right? We're still on the third period. So this will be 3P. Now, how many spaces into the P block do we have to go? We have to go 1, 2, 3 spaces in to hit nitrogen. So the electron configuration for nitrogen will be noble gas abbreviation, right? Helium, 2s2, 3p3. All right, let's do another example. Let's do sulfur. So we find sulfur on the periodic table because that position tells us everything. Our nearest noble gas that we're dealing with is neon, so we throw that in a bracket. Next, we have to identify the period we're on. We are on the third period. All right, we're on the third period. Now we have to count our way over. We start on the very edge, and we go 1, 2 spaces. We've counted our way through the S block. So this will be 3s2. We need to jump over into the P block, still third period, right? So now we go 1, 2, 3, 4 spaces into the P block. So this will be 3p4. That is the electron configuration for sulfur. All right. Now I'm going to, because time's winding down, I'm going to bring us right up to the edge of the limit of our knowledge, the limit of our ability for electron configurations at this moment in time. And then we'll take the next leap. Rocks, spot on. We'll take the next leap in lecture on Thursday. Let's do calcium. Calcium is right here. It's number 20. And argon's our nearest noble gas with fewer electrons, so we'll throw argon in a bracket. We have to find our period. Calcium is on the fourth period. So 4, calcium is in the S block. Oops, sorry, I meant to put that in green. And then we go, start on the very edge, bounce 1, 2 spaces in. So the electron configuration for calcium is argon in a bracket, 4s2. All right, now, let's pause for a second. At this moment in time, you are able to write the electron configurations and orbital diagrams for each element from hydrogen to calcium. In other words, the first 20 elements on the periodic table. You can write both their electron configurations and orbital diagrams based on what we've covered. You can't handle 21 and on yet. That's where our discussion will pick up on Thursday. If you want to practice, pick at random from hydrogen to calcium. You can totally do it. Ariana, that's a great question. That is what I would recommend. There we go. That's what I would recommend. Because honestly, as you start tackling problems and elements that are larger and larger and larger, that have more and more electrons, it's easy to lose count. The beautiful thing about the noble gas configuration abbreviation, the noble gas abbreviation, is that it keeps track of that information for you. So I think it's like the cleanest way, the easiest way. So I would recommend using that to write all your electron configurations from here on out. All right. All right, that brings lecture today to a close. We'll pick up with the enigmatic element 21, scandium, on Thursday. I will see half of you in lab in about 10-ish minutes. And I'll catch all of you next Thursday. Later, dudes.